So let's dive into the polar coordinate system. Now you may have heard about the Cartesian coordinate system, and you may have learned it in class 10 or 9th or 7th or 8th. Anywhere, it doesn't matter. And the Cartesian coordinate system is like this. Here are two axes that we know. One is the x-axis and one is the one is the y-axis, right? You know this. Now okay, so in this coordinate system you have learned how you define the position vector of any vector, like a position vector r. If it is, say, a particle is there at some point p, like here, and it is at some point. Okay, now you want to define a position vector from the origin like this. So how you do move it? You move this vector, that is x I cap vector, I cap units. What is I cap? See, I cap, j cap and k cap, these are the basis vectors or the unit vectors of this Cartesian coordinate system. You know that this is very basic things. So what you write as r vector over here is x I cap plus y j cap, right? If it is in x comma y some coordinate system. Okay, so you go this side, that is y j cap, in j cap direction. So you know this very basic thing, that is writing a position vector in Cartesian coordinate system. But today we are going to do something a very bit different. Today we are going to look into the very amazing structure of polar coordinate system, and I bet it will be one of the most interesting thing that you have learned till now. So let's get into polar coordinate system. What is in there in polar coordinate system? Means how are these things defined, and what is polar coordinate system? Okay, so if you have read anywhere in your life like complex numbers, then you must have known that to define a complex number at some point, if we go from coordinate system, we take the argument, that is the angle in positive direction. This angle is taken always in anti-clockwise direction, that is increasing angle, and if we take it in clockwise direction like this, then it is called the decreasing angle. So please keep this in mind, this is very important. Okay, so if this is, suppose this is the origin, and let's remove this. So you want to define some point over there, then what we used to do, we used to go this side, then this side, right? First this side, then we used to go this side. But later what scientists and mathematicians thought, the smart peoples, they say no, we won't do that, it is too clumsy for us. So what they did, they found a very smart version. They told that, hey, what if I go to this with making an angle? They defined a length r and an angle theta, that I will move this with an angle, making an angle theta directly to that. That is much easier. Why? Because if you suppose you have a circle, though it is not it become an ellipse. Just a minute. You have a circle like this, and you want to move along this circle, and the particle is moving along this circle, and you have to define how this is moving. And every time you will go through that Cartesian coordinate system, it will be very, very difficult. If you need to go to x like that, and then you need to go to y like that, and that is going to be very difficult. Go to x, then y, that is difficult. First move to x, then move to y, then here if you want to reach here, then you have to move to x, then y. So these are very much tedious and difficult things. So people thought, why to do that? Why on earth even do that? Right? So, 1 minute. Let's remove these things. Let's clear the space so you can view it very nicely. Okay. So in polar coordinate system, what we do, what is the need, and what we actually do in polar coordinate system. We need to learn about that, right? Okay, so let's get into that. The basics are done. Now let's move into the polar coordinate system. Okay, so in the polar coordinate system that I was talking about, we have this kind of axis. Well, this is a bit tilted. Let's make it straight. A straight axis is always looking good. Okay, now if you want to go to this point, what I was and we were talking about was very interesting thing, that we will move to this with making an angle theta. Fine, I have no problem with that. But then how do we define our position vector now? How do we define our position vector now? Can we even define it with respect to the Cartesians? What our I cap becomes and what our j cap becomes? Well, let me tell you. In this sense, if you take the position vector with respect to the Cartesian coordinate system, you will get x I cap plus y j cap. But what is the x? This distance, right? I'm going to redefine it. I'm going to say that, hey, this is actually r cos theta. Fine, this is very basic, and this one is r sin theta. Obviously, you don't have any problem with that, right? So now if you move this right over here, so what we can say is this x over here and this y over here can be replaced with what we have just found. So we say that r vector is actually r cos theta I cap plus r sin theta j cap. Well. Okay. So I can understand that r cos theta is the x thing, that x direction thing that we are doing in our Cartesian coordinate system, and that r sin theta is kind of that y direction thing that we are doing in our Cartesian coordinate system. I can get it. Now, one more thing that we can do is we can take the r common, and we got the most interesting thing that you will ever get in this polar coordinate system. Well, there are also more interesting things, but this is still now. Okay, so what we got is r cos theta I cap plus sin theta j cap. What does that even mean? See, this thing, oh, okay, so this thing is actually the magnitude of the position vector. This is the magnitude, and well, so this is actually the direction of the position vector, isn't it? Isn't it the direction and the magnitude? Obviously this is the magnitude and the direction. Well, then what next? You must have known that if you want to write any vector in this universe, say this is a vector A, this is some vector A. If you want to write, then what you will write? You will write the magnitude of A and then the direction, right? Any vector in this universe, anything, any vector, it can be a position vector, a velocity vector, acceleration vector, they all have one thing in common, that is they will have a magnitude and one direction and nothing else. Okay, so this is a very basic thing, right? And now if you tell me that, so how does a vector actually change? I mean, how do you define the change in vectors? Well, come over here, let me tell you how vectors actually change. Well, so if there is a vector, suppose a vector, let me draw it, a vector, then how does this change with respect to time? Means, how do I know that is changing with respect to time if I do the calculus derivative and all that? Well, let me tell you, a vector has both a magnitude and it also has one thing that is known as direction. So both can change. One can change the magnitude. If the magnitude changes, suppose the direction doesn't change. If the direction changes, suppose the magnitude doesn't change, or both are changing. in these three cases a vector can change. So how we will define that change, how we will set that change? So let's get into that. Okay, so how we will define that change? Well, if you take the derivative of any vector with respect to time, say I'm taking this derivative, then what I can write is this vector is actually its magnitude. I'm not giving that magnitude thing. Oh well, let me give. And its direction. And do we know the product rule of derivative? Do we know? Yes, we know that. And therefore we can write this is actually the magnitude and the change in the direction, and keeping the magnitude change and the direction constant. And this is how a vector changes with respect to time. It can change in its direction, or it can change in its magnitude. Right? This is really very basic thing, and there is nothing so complicated rocket science over here. You can get it, I hope. Now then you may tell me that, well, wait a bit, let's look back. In the Cartesian system, when we had our position vector, we used to write x I cap plus y j cap, and this was our position vector. But then if we have, say, something like that with respect to time, say 3t square I cap plus 6 some alpha j cap, 6t alpha j cap, then that time when we did the derivative, we didn't take into account this I cap and j cap. Why is that so? Why didn't we take the I cap, differentiate the I cap and differentiate the j cap? We only did these coefficients over with respect to time and not the directions. Well, let me tell you, you actually did that. But actually what we did in our schools and most of the textbooks, it doesn't mention that we are actually differentiating that. But what is happening is that when we differentiate this quantity over here, this quantity over here is actually becoming 0, and so we are getting this magnitude version. How? Why 0? I don't trust you. Tell me why it is 0. Well, I'm telling you. 1 minute. The I cap, j cap and k cap, or here we will get into account like r cap and theta cap. Okay, we will get I cap, we will get j cap, we will get k cap, we will get r cap and theta cap in polar coordinate system. These all are called as the unit vectors or the basis vectors. Okay, now basis vector is is actually something different that you will get in upper higher studies or in linear algebra or something else. But unit vectors, why it is actually because the magnitude of this I cap is actually one unit, or this j cap it also, k cap it is also, r cap, theta cap, whatever you say. Okay, so this is why it is unit. Unit means 1, and so its magnitude of this is actually 1, this vector, and so we take the direction. And do we remember that the direction of these unit vectors, direction of unit vector is actually always constant? Otherwise, if it was actually changing, say this time at t equals to 0 our I cap was this, and at t equals to 1 it became this, then the coordinate system would have failed. We need to change the coordinate system every second, every tiny amount that has elapsed. So it is not possible, right? This is not feasible. So we have defined it to be a constant, and as it is constant, when we take the derivative that we are actually doing over here, when we take the derivative of this thing, what happens is that this actually becomes 0 because this is constant. Got it? Very, very, very nice thing that we generally don't think of while doing the math. But you must know what is happening, right? Well, let's come into our polar coordinate system. Back into the polar coordinate systems. We have talked about all those unit vectors. Now, what are the bases in the polar coordinate system then? Can we define the basis vector in the polar coordinate system? Yes, we can. If this is our polar coordinate system, you say this is our polar coordinate system, then you can define the basis vectors also. What is that? Tell me. I want to know. Okay. So this is, suppose, the position vector, say r cap, r, okay, and it making an angle theta. Fine. Now what you do one thing. You put a small parallel axis over here. What is it? Well, I'm telling you, you just wait a bit. If there is a particle over here, then you put this. Okay, I have put in that. Now, the r cap, what is that? That is the direction of this position vector in polar coordinate system, right? So this will be pointed in the direction of this vector. Okay, so this direction is of the r cap. And what is theta cap? It will be perpendicular to this r cap. Since it is in this direction, we are taking increasing, that is anti-clockwise we take increasing, and if we take it clockwise, then it is decreasing, that I have told you. Then this is what you are going to get. So if I refine the diagram a bit, then it will be like this, and this is the direction, it's making an angle theta, and this is the direction of theta cap vector, and this is also making an angle theta. Why? This is actually corresponding angle. This is parallel to that this one, so it is a corresponding angle, so that is also theta. And if that is theta, this is 90 degree, so this will be 90 minus theta, and that is theta. So what we get is that our r cap with respect to the Cartesian system, we can then write is cos theta I cap, obviously, plus there is also one thing, that is sin theta j cap. Okay, and if you look into this theta cap, you will see this is actually minus sin theta I cap plus cos theta j cap. So this is the conversion of the basis vectors or the unit vectors from polar coordinate, if you go into polar coordinate, to Cartesian. Fine, I have understood that. I got the fact that this is what and what is what. Well, if you understood that, then before moving ahead into our series, what we do, we define a very common notation in physics that you will be encountering in your, if you continue with physics, you will be encountering these notations, that is dot notation. So this is known as dot notation, and I'm just telling you what this thing is. You will encounter it in many places. So what is dot notation? When we write some derivative with respect to time, say our x is changing, our y is changing, something is changing with respect to time, say x is changing. So when we write this derivative, we need to write all those things, d, dt, and it takes a lot of space, right? So when we do some complex equations and differential equations, writing those things a lot of time is taking a lot of time. Actually, it takes energy. And what mathematicians found out, that if we do this d dt, this change in time, if we mention it with one a dot, it will be much more easier. What they did, if x has to change with respect to time, first derivative, then you put one dot over its head. You put a dot. If you have to define the second derivative of that x, then you put two dot. Okay, so this is known as the dot notation that we will be using later in the series. And you must know that if y was changing with respect to time, then you put a dot up of y. If y, the second derivative you want to take, no problem. You take second derivative, you will put two dots. Okay, so this is the dot notation, and this is very important. If you want to do some rigorous mathematical derivations, then you will have to encounter this dot notations. 1 minute, and it will be required in our series. So please remember these things. This is nothing very much complicated. It is actually a simplification that we write. Like to tell you the story, like in a previous days when mathematics was in its early stage, people used to write, suppose 2 plus 2. Well, 2 was also written in letters. It was not written in numerics. 2 plus 2 is equal to 4. And when they have to do so much mathematics, what mathematicians found was that they turned this plus into a symbol. They turned this is equal to, that was many repeated, they turned it into one symbol. So now when we study 2 plus 2, we just write those symbols. But where are those symbols? What are they? They are just merely a simplification of a longer notation that we used to do in our previous works. Okay, so this is up to it for today, and in the next upcoming video we will be deriving the velocity vector, the acceleration vector in polar coordinate system, and all that. So okay, I will be linking the PDF of this file in the description. You can go check it out, and if you like this video, then please subscribe and like this. And at the end, let me tell you what we are going to do is we are going to derive Kepler's laws of motion. Yes, the first law and the second law of Kepler's motion from very basic, from polar coordinate system to basic trigonometry and some basic calculus, and you will be deriving the beautiful thing that why the planets actually move in this ellipse, and why is it ellipse, where from Newton got that 1 by r square theorem, why it is 1 by r square, why not 1 by r to the power 2.5 or r to the power 3. All these interesting things will be coming ahead. So not to miss that, hit the subscribe button and click the notification bell. And once more, happy learning. Thank you.